Good morning. I think we'd like to get started with the session now. I'd like to welcome all of you to this session on using historical information to improve seismic data processing methods. A couple of administrative comments before we start. First of all, we'd like to keep all the talks on schedule. So once you see the yellow light come on the podium, that means you have 3 minutes left. So we'd like to sum up the talk at that point to leave time for some questions for the speakers. And I'd also would like to remind everyone that we have a poster session in the afternoon where we have about 15 some odd posters focused on this subject as well. So I'd like to introduce our first speaker. This is an invited talk presented by Stuart Russell, and it's Physics, Data, and Bayes for Global Monitoring.
Okay, I'd like to thank the chairs for the invitation to come and speak to you today. So we are all familiar, I think, with the International Monitoring System, which is up to 273 stations. We're focusing on the seismic ones, and our job is, given the measurements coming in from the network of stations, to produce a bulletin of events. Each event is characterized by its time, its location, depth, and magnitude, and the performance metric has these components. The recall is probably the one that matters most. That's the fraction of real events that you actually discover in the data. We're also interested in 1 minus recall, which is how much you miss. Precision is the fraction of events that you announce that are in fact real. Obviously, if you announce that events took place at every location at every time, then you would get very good recall but terrible precision, and that would not be helpful. And finally, we're interested in the location accuracy of the detected events. And this is a hard problem. There is a lot of noise. Most of the detections are false. They don't end up being associated with any real events. And because of the travel time for signals, at any given station, the signals from many events can be mixed up in their temporal order. And so it's a very complicated problem that we call data association. And the CTBTO system, which is called the Global Associator and produces an output called CEL3, has been developed over several years and still has some gap between where it is now and where they would like to be. It finds about 69% of the significant events, so that's the recall percentage, and 16 human analysts work on the output of that system along with other tools to add in as many as they can of the events that the automated tool doesn't find. The final output of the human process is called the LEB, that's the ground truth that we use, the late event bulletin. So this session is about using data, and I'm a computer scientist and I do machine learning. And here's a simple description of what machine learning does. You take data, you apply learning methods, you produce a hypothesis. And we're interested in finding the hypothesis that fits the data as well as possible while not being too complicated. And there is a long history of algorithms and mathematics behind this. And for our purposes, the data that we have is the history of previous waveform recordings and detections and the events that have been determined by the combination of automated and human processing in the LEB bulletins. And then the hypothesis is, how do you map from some new set of waveform measurements to a new bulletin? So it's a function that maps from waveform collections to bulletins, and we want to see if we can learn that function. So in my belief, this is a terrible idea. The mapping that you're trying to learn is far too complicated. The output is extremely complex because it consists of unknown numbers of events, whereas most machine learning techniques are designed to output, for example, a single yes-no value, like should I give this person a credit card, and they're just not really designed for producing very complicated outputs. Plus, if you do it this way, the learning algorithm has to discover everything we already know about geophysics. It has to learn the phase velocities. It has to even come up with the concept of a phase velocity, which it doesn't have. It has to figure out Earth geometry without any knowledge that it's even a round ball. It has to invent the notion of triangulation. None of these things are really going to be very easy for a machine learning algorithm to do. And it would take an enormous amount of data for a machine learning algorithm to do this. because it does not have the benefit of thousands of years of human development of mathematics and geology and so on. Finally, even if I did build you a system like that, you wouldn't trust the results because you wouldn't understand how it was working. You wouldn't know what physics was going into it because it was inventing its own physics. So the approach that we're taking is what's called model-based learning, where you provide as much prior knowledge of the problem as you can, and then you constrain the hypothesis space using that prior knowledge. The data then picks out the best hypothesis in the remaining hypothesis space, and then that produces knowledge that you can use to then perform the task in future. And the particular method we use for combining prior knowledge and data is Bayes' rule. And in Bayes' rule, you have a prior model, and it comes in two pieces. One describes the prior probability for the occurrence of events, and the other describes how those events produce signals. And so that's where most of the seismology and seismometry knowledge would go. The parameters of these models can be learned from data. So you're really fine-tuning and filling in the details of the models rather than trying to construct everything from scratch. And when you have a new signal coming in, you take your model and you apply Bayes' rule. The two terms on the right, P of signal given the world, this is your knowledge of seismology and seismometry. This is your prior for event locations and types and depths and so on. And you basically multiply those two, given the signal that you have, to produce a posterior distribution over what the world might be like, i.e. what events actually occurred to produce these signals. So I want to make a distinction between two particular ways in which we could instantiate this approach, a detection-based method and a signal-based method. So when you have waveform signals coming in, station processing in the traditional approach produces detections. And then the existing system goes directly from detections to a bulletin of events. The first approach that we've tried, our NetVisa system, produces the same kind of event bulletin from the same inputs, namely the detections obtained from station processing. But the way it does it is somewhat different. So NetVisa has a forward model that explains detections given events, and then it does inference to basically invert that model. We could also go the whole way. We could have a model that goes from events all the way to waveform signals, and then we could invert that using inference. And this is the SIGVISA system, which is still under development. So let me tell you about the NetVisa generative model. It has an event prior. There's a global rate of events. There's a location distribution based on historical data for natural events, and then a uniform assumption for man-made events. We assume a uniform depth prior, and we assume the Gutenberg-Richter magnitude distribution. And here's how we describe the physical process by which signals are produced. So first of all, the event has to be detected at the station. That depends on the magnitude, the distance, and the depth of the event. And then the the arrival has an onset time, and that depends on the event time, the distance, and the depth. And then there are properties of the arrival, the amplitude, the azimuth, the slowness, and the phase label. We also have to describe the detections that are generated not by real large events, but by local noise and other phenomena. So those are, on a per-station basis, we describe the noise process. So let me show you some of the pieces of that, but first let me just say this is still physics, right? It doesn't look like physics. It doesn't have curly Ds and Greek letters, and well, it does have Greek letters, but it doesn't have a lot of curly Ds, and so it's not a classical kind of differential equation model. These are really mostly empirical models, and the important part is that they have calibrated uncertainty. So if you wanted to predict arrival time, you could use physics and a voxel-based model of phase velocities and do all the propagation calculations, and that's great if you have all that data and you have knowledge of the interior of the Earth. Okay? That kind of model also does a lot more than we do. We don't predict exactly the path that the wave will take, because in some sense we don't really care. What we really care about is when it will arrive and what it looks like when it gets there. Okay? So we're making fewer predictions, and they're weaker predictions, but we need much less information to use these empirical models as opposed to the classical deterministic physics model. The other part of the physics that's really important is the compositional structure of the model. So what are the components of the model, and how do they fit together? And once you have that structure, you can refine the components as much as you want, and eventually you will end up with a classical deterministic physics model. So here's the basic structured model. We have the prior for events. We have propagation of signals. They can be detected. There's also noise, and that produces the arrival information at the stations. So I'll show you some of the pieces. Here's the event location prior. So there's a uniform distribution. That's sort of the big blue background. And then historical events are used with a kernel-based density estimation process to estimate this prior. The propagation, so travel time is the main thing you're concerned about. And we take the ISP model, and then we have a Laplacian residual distribution. And so here we have a particular station. We see that the Laplacian residual distribution is slightly biased away from 0, so a late arrival in this case, compared to ISP at that station. The detection model itself is done by a logistic regression function. So this is perhaps the place where we have the least knowledge of the physics, because which stations detect which kinds of events depends a lot on their local geology and the quality of the station calibration and maintenance and so on. So we simply basically build a historical model of how good each station is at detecting the various phases from various magnitudes and distances. So when we evaluate this kind of system, we can do that by training on some data and then testing on held-out data that the system hasn't seen. And we compare the output of NetVisa against the LEB, assuming that the LEB is ground truth. And we'll see in a second that that's not quite the case. So here are some results. This is the fraction of events that the system fails to detect, and we would like to keep this as low as possible. So the red bars for different magnitude ranges are for the existing UN system, and these are the results for NetVisa. So you can see there is an improvement as a result of using this approach. We can also look at the geographical distribution of hypothesized events. So this is for the cell 3 list. The yellow stars are the LEB true events, and the red circles are the cell 3 hypotheses. And you can see that the geographical distribution looks somewhat unhealthy. There are lots of events being proposed in places where they don't really occur. And this is the corresponding diagram with blue squares for the NetVisa events. You see that out of the ones that we miss, for example, there's a little event that we missed. A lot of them are actually in the ocean, and that's because we don't use yet the hydroacoustic data. We also find a lot of events that don't exist in LEB. And initially we thought, oh, those are just mistakes. So that contributes to a lack of precision in the measurement of the performance of our system. Now, when we went to look at some of the regional catalogs, for example, in Central Asia, looking at the catalogs from Kazakhstan, there's 101 events during this period, and NetVisa found just about 50% of those, and in LEB only about 34% of those are there. So that difference, those extra events up here, are ones that we got marked wrong because they weren't in LEB, but in fact they are real events. Okay? So it's possible that by using NetVisa we'll actually get a better output after the stage of human processing than the UN is currently able to do. So here's one example. This is an event in Mexico, which is in the NEIC catalog. And here on the left, we show a heat map for the posterior probability that that event occurred and its location. And this is the NetVisa location. This is the NEIC location. And there was nothing in either cell 3 or in LEB for this event. And for the DPRK event of 2009, we do about as well as LEB with the same number of associated detections and a very similar location. So there are lots of improvements that we would like to make to the NetVisa model. So as I mentioned, we're adding the hydroacoustic sensors. We're going to have, rather than assuming the independent depth and location prior and a uniform depth, we're going to have a joint depth location prior with more detail on the depth distributions. Aftershocks are very important. So the current model assumes a uniform Poisson process, and in fact the rate of that process changes depending on the history of nearby events. So we can model that in the system quite easily. Right now we assume that the travel time of different phases from the same event is uncorrelated, but in fact there is a significant correlation, and we can model that in the overall probability model. And finally, this is probably the most difficult thing that we're planning to do with NetVisa, is to consider adding a moment tensor variable. So rather than just assuming that the event is a point, it actually has a direction and other things. So, and that would explain the anisotropic detection probability and amplitudes that are arriving at the stations. And then I'll talk a little bit about the SIGVISA model, which is modeling the waveforms, so generative model of waveforms given events. So this is something that people are starting to make really great progress on in the classical physics with voxels and propagation equations and so on. But we're trying to do it using more statistical approach where we're simply trying to predict the shape based on what we know about the event. So the model has quite a lot more physics than NetVisa. We're trying to predict the shape. We have frequency-dependent amplitude and coda decay rates. We're looking at having path-dependent travel time and path-dependent signal shape. So we're actually looking at detailed parameters for those predictions that vary according to source location for a fixed station. The advantage of doing it without detections is that we no longer have a detection threshold effect. So in principle, we can find extremely weak signals, and we can combine the weak signals from many stations to get a fairly confident hypothesis. We can also model overlapping signals, which is a very significant problem. And things like waveform matching and double differencing actually fall out automatically from the Bayesian analysis. We don't have to write special algorithms to do these things. If you have the right kind of prior, then just applying Bayes' rule gives you this for free. So here's a little bit about what the model looks like. So we say that the observed envelope for the arriving signal consists of the background noise plus a template whose parameters depend on the size of the event, the distance, and so on, and then a path-induced modulation. So we call those the wiggles, and the wiggles are path-specific. So if you have a doublet, an event in the same location again, you will get the same wiggles in your event. In your signal. So here's a real signal. Here's a best fit template for the P and the S. And then if we take that template and then use our model to generate a signal from it, then we get something that looks actually fairly similar. So it's important to keep in mind that when we have a template here, we're not saying this is the exact template. There's really a distribution over the templates for a given signal. And then given a template, there's a distribution over the signals that you would expect to see, because we're not predicting the wiggles deterministically, and we're not predicting the noise deterministically, so there's a distribution over what the signal would look like given a template. Okay, so a little bit more about the template shapes themselves. So there are really two parts of the template. How big is the initial onset, and then what does the coda look like? What's the decay of the signal? And so we have decay rates that depend on the frequency band and on the source location and on the station location. So here's some data from Kevin Maida, who's a member of our project and an expert on this subject, showing that for different frequencies you get different rates of decay of the coda as a function of time. So if we look at the coda decay rate for various events and we see, well, maybe coda decay rate depends on distance. Maybe when it's very close, the decay rate is slow, and when the event is very distant, teleseismic, perhaps the decay rate is very fast. So here's some empirical data, and for one station in Australia. And you can see that, well, there is kind of a downward drift. So down means down here you have rapidly decaying coda, up here you have very slowly decaying coda. And it's true that most of the slowly decaying codas are for nearby events, or when I say nearby, that's 2,000 kilometers. And then the decay rate seems to increase as you go to the right. But that's pretty messy. It's hard to build a nice predictive model out of data that looks like this. But if you go and look at specific regions, all we really need is that the coda decay is fairly consistent when the events come from a small region and come from roughly the same depth. Okay? If that's the case, then we can build a predictive model which we can then invert to understand the signals we're getting. So here's the station, and here are two different regions at about the same distance. And then going back to that plot, we see that the events from the green region all have very slow coded decay, and the events from the red region have quite a bit faster decay. So there's consistency and differentiation between regions, which is what we need. So here's just an example. This is from the slowly decaying region, the green region, and this is from the quickly decaying region, the red region. Okay. So that's the template shape model. And then what about the wiggles? So we're basically assuming, which is a fairly strong assumption, that the wiggles, the path-induced modulation, vary smoothly according to the location. So if you move 1 or 2 or 5 kilometers from the original location, you should get a somewhat similar wiggle. And we can model that with a Gaussian process, which is statistical language for Kriging. So there's a Kriging model on the modulation parameters. So for example, if we use a Fourier decomposition of the modulation, then the Fourier parameters vary smoothly with location, and the Gaussian process describes the distribution over the way in which the Fourier parameters vary with location. So if we generate from our probability model the signals coming from nearby events, then they look very similar, and from distant events, they look quite different. Okay. And this just shows how you can predict the waveform. So here we have changing prediction location. You can see the location going up and down this line. And the blue waveform is the actual measured location at the green dot, and the red is the predicted. And you can see that when you get to around the true location, you get a waveform that looks very similar to what was actually found. And we can use that to predict locations of events from single station detections. Okay, that's the end.
Thank you. I think we have time for one question. Oh.
Yes. What do we do with the events that are new? So when you're far away from any previous events, the Gaussian process prior will basically become the purely physics-based parametric prediction for template shape. And you only are able to predict the wiggles accurately when you're close to some previous event. Okay, so you'll just have a much vaguer prediction about what the signal will look like. So we will locate it in the traditional way, and in between, then we'll locate it in a way that's a hybrid between the traditional way and the doublet detection way.
We need to move on now. Right. Thank you. Thank you very much for your presentation, Dr. Russell. All right, our next presentation will be fast estimation of empirical distance and magnitude from a 3-component seismic station using machine learning techniques, and it will be presented by Luis Ochoa.
Okay, good morning. Thank you for coming. I'm going to talk to you about the things we're doing in Colombia, where we have a very sparse network, seismological network. So we are trying to do this with only one station, one single station, using machine learning techniques, something similar to what we saw before, but not with Bayes, with another machine learning technique, which is super vector machine. First, I want to show you some things about our city. In the Sabana de Bogotá, is the most important social and economical center of Colombia. And almost a third of the population is there, and 40% of internal brute product. So, as you can see, this is a very vulnerable situation. And any seismic event with a really relative high magnitude can cause a lot of damage. And we have been recording seismic events since 1743. More of them, obviously, only descriptive, but in the last 20 years, we are acquiring a lot of information. This is a plot of our country, Bogotá, Colombia. As you can see, let me see, it's about this place. These are the foothills of the Llanos foothills. And we have a subduction zone in this area, So, you know, this is a very active area. This is a very active zone. And we are going to try to use only one station in this case. This is the faults around Bogotá. And the idea was to use some kind of machine learning techniques that have been used before, like, for example, detection and classification of seismic signals with neural networks, phase picking, also neural networks, the Earth structure and tomography using some genetic algorithms, earthquake hypocenter location genetic algorithms, and inversion of source parameters, genetic algorithms, simulated annealing, and a lot of other techniques that have been used. So in this case, this is our problem. We want to characterize characterization more or less in the near real time using only one single station. This is just because we have a coarse network, okay? And the way can be, for example, using support vector machine. What does support vector machine? In this case, this is an example of classification where in this case, I want to classify between blue points and red points. So I can't, it's impossible to find a linear function which can separate those two. But if I try to combine these two variables and make a new variable with some function with those two and get a new variable which take my data to a new space, in this case, for example, I can square both of them and I will have something like this. As you can see here, I can do a linear function to separate the two variables. This is more or less how the support vector machine works. And what we use is support vector regression to find magnitude, find distance, and find azimuth. How do we do that? So this is the seismic event. In general, a seismic event has a classical processing, location, and calculation of magnitude, a classical way. And this goes to files, is kept in somewhere. And this is what I call here desired output. This is what I know of previous events. And what I do with the support vector machine is take this information in some way, I need to find some variables which describe this event. In this case, what describes this event is something related with the seismic signal. I will show you some of them. And with these descriptors and with this output, what I do is training a support vector machine where I'm going to teach in a way that system with this data, this is what I have, this is the result. And we train them, so and the new scheme is with the seismic event, goes to support vector machine, it calculates magnitude, distance, and can let me give an early warning here, but also it goes to classical processing and a kind of feedback can be considered here. Okay, this is an example of we did there. Bogota is here. We have the three. As you can see, it's a very coarse network. And also because this is, there are a few three-component stations, and Rosal station, which is here, is the one who is with three components and no more than 2 or 3 in this picture. We do the next. This is we call seismic wave explorer. What it does is take all the seismic events and calculate some descriptors, as I call. In this case, this line is linear interpolation of log of time and amplitude in this signal of the maximum amplitude, which is an envelope in the 3 signals. So what I do here is to make a linear function, log, and this is only the slope and the intersect. And this data plus, plus, this is the attributes. This is a detail of the previous figure. And, oh no, it's not here, but we also use the polarity, oh no, it's next, okay. In this case, we did it with 10 seconds, and this is magnitude. The support vector regression needs an exponent of the kernel function, that function that I showed you in the slides where I was explaining support vector regression, has an exponent, and it has another term that is called a complexity parameter. In this case, we do many experiments to try to find the lowest mean absolute error here, which for magnitude is 0.16 units of magnitude, and for distance is about 7.5 kilometers, taking into account that we have about 120 kilometers of distances between 0 and 120 kilometers. Then we use something additional for direction. We try to have a polarity function here. This is only the number of events in one side and in the other side, each half second here, and we take into account that, and that's a linear function as you see here and here for each component, and this can give us an idea of direction or azimuth. Look here, it's about linear here. All these parameters, all these descriptors are not exactly invented by us. This has a previous work. For example, the linearity of some magnitude event. The magnitude with the 10 seconds magnitude is for Wu in 98. And this kind of descriptor, which is a logarithm function of the envelope that is related with distance, is a work of Odaka, 2003. And it has a lot of knowledge behind for all these descriptors. As we saw in the previous presentation, you have to put some previous knowledge for make these kind of schemes of machine learning or data-driven analysis can work, okay? Then, with this data, we can find, in a way, the azimuth or the difference in east and north to try to make a location. And what I'm going to show you are some results. This is maximizing covariance matrix. Is another descriptor we use, which are these coefficients of this function. And with that, this is what we obtain. This is calculated, and this is the real azimuth. This is not a very good model, as you can see, but we are trying to make it better, to improve this in a better way. This is using all the events magnitude more than 2, more or equal than 2. This with more and equal than 2.9, excuse me, 3. Azimuth and magnitude. In magnitude, we are more near to reality. As you can see, some kind of dispersion, but we can find more or less a correlation here with the magnitude, total magnitude, using only 5 seconds of signal. The important thing here is what you are using here, 5 seconds of signal. So it's about 5 seconds after P wave onset. Distance has the same problem with only 5 seconds. The first graphics that we saw before were with 10 seconds of signal. What we are doing time by time is reducing this time. And what is next? Next is that we have to try to improve these descriptors to have better pattern recognition model to make a better support vector regression model. And that's what I want to show to you. Thank you very much for your attention. And questions maybe?
So we have time for a few questions. Okay. All right. Thank you very much. Okay, our next presentation is titled Continuous Large-Scale Processing of Seismic Archives for High-Resolution Monitoring of Seismic Activity and Seismogenic Properties. And it will be presented by Felix Waldhauser. Yes, you can forward by clicking the mouse or going up and down.
Thank you.
Well, thank you. Thanks for coming, and thanks for the invitation. What I'm going to talk about today is how we can harness the tremendous growth in digital seismic archives over the last several decades to radically improve on the resolution with which we can monitor seismicity. I'm going to show a real-time operation for Northern California in the first part, and then in a second part, our effort to apply those tools on a global scale. What you see here is a histogram of the number of globally recorded earthquakes as listed in the ISC catalog. You can see that from the 1970s, where there are about 10,000 earthquakes a year, we are now adding about 300,000 earthquakes in more recent years. So that increase is, of course, not because we have more earthquakes. It's because of the rapid expansion of the digital seismic network and the improved quality with which we record these events. If you go to the IRIS DMC, you see an exponential growth too there in the amount of seismic waveforms that are stored there. We are now about at almost 200 terabytes of data that is stored over there. Now, despite this tremendous growth and wealth in new data, we still don't know where exactly those earthquakes locate in the Earth crust or mantle. And this graph here shows the yearly average in location uncertainty as listed in the ISC catalog. So you can see it's between 10 and 20 kilometers. And didn't really change over the last several decades. So 10 to 20 kilometers, that's roughly the rupture area of a magnitude 6 earthquake, but greater than the thickness of the oceanic crust, for example. Now I have to mention here that the formal errors for location errors are only known for a fraction of the events in the catalog, and in many cases, depth is actually not even resolved. If we go to regional catalog, such as the one produced by the Northern California Seismic Network, the errors are substantially lower. They're in a few hundred meters to a few kilometer range. But still, that's a magnitude, roughly the rupture area of a magnitude 4 earthquake. The reason why the uncertainties are much better is because typically you have a seismic station very close to any given event. We have now, when I mentioned magnitude 4 earthquake is 99% or in Northern California actually below magnitude 4. And so for many events, we lack the resolution at the scale of individual earthquakes. We have, in the last several years, we have put significant effort in trying to bring those errors down, both in existing catalogs and for new events in real time. So we have been producing and updating a so-called double difference catalog, which relocates earthquakes, multiple earthquakes at the same time, simultaneously, rather than locating earthquakes one at a time as done by most seismic networks. So we are almost finished with an update of the 2011 catalog. So the seismic archive goes back to 1984. The NCSN runs about 900 seismic stations, includes about over 500,000 earthquakes, 20 million seismograms, and 10 million phase picks. So we use cross-correlation tools to reduce the pick errors. We are about 66 billion correlations that we carry out on those waveforms, and we retain about 2 billion delay times that we measure from similar seismograms, similar at a correlation coefficient of 0.7 or larger. We combine the correlation data with the pick data to resolve the high precision event separation. And for that, we solve about 50 billion double difference equations. The catalog we're producing is about 10 to 100 times of better resolution than the existing one, sometimes even 1,000. Typically, the errors are in the relative location errors are in the range of tens to hundreds of meters. You see here on the left is a comparison between the original network catalog and the double difference catalog in a complicated area where the Calaveras fault intersects with the San Andreas fault. And you can see the improved resolution we get along the near vertical strike slip faults. We also remove some of the artifacts that's seen in the network catalog. Now, what we're doing now is we are using this background archive to locate new events with high precision relative to the double difference catalog. And the only thing I want you to take from this flowchart is that when we do that in near real time, that we are constantly pulling and pushing from and to the DDRT archive. So once we have a location from the NCSN, we start comparing that new event or the seismograms to the archive, correlate the seismograms, relocate the event, and then add it to the double difference database. And then what we need to do every now and then is to do a periodic relocation for a simultaneous inversion of all the data. So this system, DDRT, it's a system on a disk approach, so everything is on one disk, so you have relatively fast access to the to the archives, and it's currently running at Lamont with data feeds from the Northern California Earthquake Data Center, and we are also implementing it at the USGS in Menlo Park. So what I want to, the next few slides, I just want to show you what kind of information we are getting out of that DDRT system. This is taken directly from the DDRT website. So if you go to this URL up here, you can go and explore that tool or the data. So what we want to push here is to have the new earthquakes with high resolution 3D interactive tools to look at the new events relative to the past seismicity and everything in real time. So the example here, what I'm showing here is a magnitude 4 earthquake on the Haber Fault that occurred in 2011, October 20. It was widely felt. So if you look at it in the 3D view here, you can actually rotate it into the fault plane, and you can see immediately that this magnitude 4 event occurred on the main strand of the Hayward Fault. Now this is important to know because from this you can infer the rupture plane. When you look at the routine location, the single event location here, it is about 1 kilometer off the fault. So it wasn't quite sure whether that's a Hayward Fault event or whether the earthquake was on a parallel strand. What we're also trying to develop is a Google Earth capability with cross-section capability so that we can relate the Google Earth information with depth of information we have from the seismicity. And then we're producing spatiotemporal snapshots from selected faults. Here is the Hayward Fault and a map view and a cross-section. And the next few slides are going to zoom into this magnitude 4 earthquake and to show you what type of resolution we are getting in real time. So the blue circle, the biggest circle, is the magnitude 4. There's an approximate rupture area, the circle size. And the background in gray are the background catalog back to 1984. And you can see that the magnitude 4 earthquake was followed 1 day later by a magnitude 3.8, and then 1 week later by a magnitude 3.6. They all have abutting source areas. And the aftershock activity then went down to what we call a streak here, which we inferred to be the brittle ductile transition. And it jumped quickly up here later, and then it came back into the streak and died out. Now we can go back in time and see and we find that we had a very similar sequence in 2006. The same that sequence started up here again and moved downwards into the to greater depth into the streak. Now, in 2002, we published a paper arguing that this part here is creeping and this part here is locked. Now, this situation here might be more complicated now that we have a 2006 and 2011 sequence. I guess the question is, what is this part doing here? If it's frictionally locked, it could be rupture in a magnitude 4.5 earthquake or so. And the worrying issue is could that be the beginning of something bigger, rupturing the northern Haber fault? So you can see from this kind of analysis that the DDRT framework is not only here to produce high precision locations, but we can do a lot of more analysis, especially going at changes in seismogenic properties. We can track a short-term evolution of stress concentration, like I just showed you in the previous slides. We can image active fault plane and rupture area from rapid, precise aftershock locations. Or we can track changes in recurrence intervals of repeating earthquakes. And from that, we can infer on the loading rate or creep rate of certain specific faults. That's a project we're currently working on. Another thing that this platform enables is the use of cross-collation as a detector for new events. Now that we have all the sample seismograms at our fingertips, we can run the continuous data stream over those samples and run a detector on the correlation function. So that's shown here for an earthquake in China. That David Schaff has mostly worked on those detectors. So essentially, you cut out the seismogram from the main shock and then run the data stream over that sample. And then you can see from the correlation function, here is the autocorrelation of the main shock, and then you have a second detection of a second event that's buried in the coda of the main shock. Those are the three components, and you can verify the detection on each of those components. We have applied that to Parkfield, just using 10 samples across the fault surface of the Parkfield section, and what we got is we got about 700% more earthquakes detected about 1 month after the 2004 main shock. So that's about two months of data around the 2004 magnitude 6 main shock. So there's great potential here, not only to improve the ability to image fault zones, but also to expand the catalog down to lower magnitudes. So I want to, the rest of my time I want to spend on our effort to go global. We are currently reprocessing the combined archives of the ISC, the EDR, and EHB bulletins, together with waveforms that we get from IRIS. Those archives include about 3 million earthquakes. So the situation here is a little bit more difficult than in California, mostly because of the station distribution, because of the large number of earthquakes that have an unconstrained depth, and other issues. So what we do, the procedure we are following is we are establishing a baseline using a double difference EHB catalog, and then relocate each event in the ISC relative to that baseline using a single event double difference algorithm, and then do a simultaneous relocation of all this PIC data to improve the relative location in these catalogs. And from those, we pick the pairs for which we want to do the cross-correlation measurements. And the final step will be to simultaneously invert both the PIC data and the correlation data for a final catalog. And then eventually use that catalog to implement into real-time platforms similar to the DDRT system. Now these procedures we have mostly developed and tested in the Sumatra subduction zone. I'm going to just show you an example of the type of resolution that we are hoping or we are expecting to get on a more global scale. What's shown here are 20,000 earthquakes in the Sumatra subduction zone, 14,000 of which are aftershocks of the 2004 magnitude 9.1 earthquake. What we're using is essentially all bulletin data, phase peak data that we can get, and that are observed pairwise at a common station. So that's just a selection of that data. We get first arriving and late arriving P and S phases. On top of that, we did the correlation measurements for first arriving P and S phases, including the core phases. Now, the core phases are important because of the downgoing ray path. They constrain relative depth very precisely. The results from the correlation measurements are shown here on the right side. You can see that that we have quite large areas where the correlation didn't perform that very well, but there's like spots here in the back arc or the Nicobar swarm that have quite a large number of correlated earthquakes. You actually see that situation in other areas too. For example, Haiti, the aftershocks of the Haiti earthquakes didn't produce any correlated aftershocks, so any correlated seismograms. So it is important to combine both the PICs and the correlation data to get the best out of those two catalogs. So I'm going to focus on a very small area here of relatively large aftershock activity just north of offshore northern Sumatra. This is a study we did just a year ago. What you see is here is northern Sumatra here. The red lines are the active faults. The Differential is over here. Sumatra fault is over here. The yellow patch here is the Asia Basin. And you can see underneath the Asia Basin that we have this streaky behavior of the aftershocks, about 70 kilometer long, pretty narrow in width. And if you look at the depth section looking to the northwest, you see that the majority of earthquakes locate on or near the interface and then in the overriding plate. Now we can see from the location of the larger event and the correlated event that are shown here in red that they appear to reactivate pre-existing imbricate fault system. Especially one fault that we can track across the whole cluster here. We also see that on other cross sections is what we infer as a mass display that surfaces near active thrust fault mapped after the earthquakes, after the main shock. And so when we look at the temporal signal, then we can see that the earthquakes are rising from periodically rising from the plate interface. So our interpretation of this is that these aftershocks streaks are controlled by inherited seafloor fabric. So when this water entered those seafloor faults, they got subducted. During the main shock, the water got expelled into the overriding plate and caused rose and caused brittle failure on the imbricate faults. So the point here I want to make is that with the improved spatial resolution, we can now reveal temporal signals, and which helps us to understand seismogenic processes hopefully eventually on a global scale. So I want to end with a few comments on the computational aspects of this kind of processing. Up to now, we did pretty okay with using just traditional multi-core computer clusters. We typically use about 40 cores, relatively fast CPUs, but nothing really fancy. But if we move global scale or high density application, like aftershock surveys that produce 100, 200,000 earthquakes into the real-time environment, then we may have to think about a few other solutions. And one of them, there's a couple of them here we can use. We're currently using PETCs for inversions. We use graph theoretical approaches for the searches, the network of delay time links. We're working on with ISTI, working to get GPUs to the DDRT system. This is especially useful for time series analysis, and then the searches, they go much faster. And finally, a big drag on the performance is the I/O reading and writing out seismograms, but we currently do that on our RAID system, but if we move to solid-state drives, we can significantly increase the performance. So I leave the summary up here, and I'm happy to answer any questions you may have. Thank you.
I think we have time for one question.
So we start from the routine location. So if there's nothing that correlates, which happens every now and then we just leave it as at the original location. But then when you have a second event that locates close by, and then we use that to compare with the first event. Or exactly, yes. So Haiti, for example, there was nothing there before the main shock. And so all we did is we looked at the aftershock distribution. So the more aftershocks you get, the higher resolution you get. You build up your density, essentially.
I think we need to move on to the next slide. I think it's fantastic. Oh. Okay.
Thanks, Ross.
Thank you very much.
Okay, our next presentation is Data Intensity Discovery Methods for Seismic Monitoring. The talk will be given by Paul Richards.
Control L. There we go. Click the button. So my thanks to Bill Junick and Dave Harris for organizing this session, and to Felix, who preceded me, and David Schaff, who have pointed the way and are taking us forward to a new era of what I like to call precision seismology, elevating the quality of almost everything that we do in the study of earthquakes, because we need to know where they are. In particular, this type of work addresses a grand challenge, as it was reviewed a few years ago in seismology, emphasizing that penultimate paragraph there, accurate relocations down to low magnitudes on continents at least, with precision at the fractional kilometer level. But of course there's an anomaly as we see what is preventing us from this current ability, namely that the way we locate earthquakes, as published in global bulletins at least, for the most part, although almost everything else has changed in geophysics, is based upon an algorithm that goes back a little more than 100 years. Here is the key publication, indeed 100 years ago in English, Geiger's method. Locate seismic events one at a time with phase picks using somebody's model of travel times. And that's, amazingly, in 2012, what we still pretty much do. And at one level, it has served us very well. Here, for example, are the ISC locations going back since 1960. And as Felix reminded us, it's actually you might say 3 million events, because additional to the locations that the ISC generates itself, they are also putting out for the research community an almost equal number, just passing forward those that are generated regionally, a large fraction of them in Japan. So how can we get away from Geiger's method? And the key is to work with historical data, as Felix just showed us. And this presentation is a report from a collaboration. Here's a graphic to show that I'm not afraid of logos. Here they are. I won't use them again. Yeah. So, okay. I will briefly, unfortunately, in time constraints, say a little about what the Penn State component of our collaboration is doing, and then go on more to talk about some of the interactions between those of us at Lamont and at Sandia, where a group has put together a really substantial computational facility and working with the database management skills appropriate for what national laboratories do. So starting then just briefly to make a mention of the Penn State group, recognizing that 70% of the events here are oceanic, the focus of the Penn State component of our collaboration is indeed currently the ridge transform system. And for example, with NEIC locations for the chain fracture zone and Romanche, the improvement in getting relative locations, in this case, has been achieved by using cross-correlation of the fairly long period Rayleigh waves and comparing neighboring events and so on, doing that also. Another location map, as you see in the index, the box there. Let's focus on it for the Panama fracture zone. The NEIC locations in this map view of that north-south fracture zone, and the improved locations. Now, getting into the details, the question would be, in this case with long-period Rayleigh waves, the work being done by Mike Cleveland and Chuck Amon, with long-period Rayleigh waves, precision in measuring relative times, and this is what we need to do to figure out how to do this on a global scale, to work out what are the rules to achieve what we want to provide. And the last 3 lines here are the most important part of this graphic. So there is more on this subject to be presented in a poster this afternoon by Mike Cleveland. And let me also mention this afternoon, I wish I had time more to talk about it here. Of course, a lot of this work with cross-correlation is about measuring relative arrival times accurately. But as this poster shows, it is also available for us to measure relative sizes of events much more precisely, much better than comparing station magnitudes as they scatter about a mean and so on. So now I had to go back to the main theme, and just to remind you some of the achievements of Felix Waldhauser and David Schaff, work published 4 years ago, a tremendous achievement for California. And the question with this type of work is how to take it forward to even broader areas. In the present case, the achievement includes, as Felix also just showed us, on the relocated, much more precise relative locations based, in the present case, on about 900 stations in California. And we ask, can the community achieve on a global scale like successes with a couple of important wrinkles? We don't have the same station density globally, of course, and we would like to add automatic detection for broad areas. That means using templates and searching continuous data for cross-correlation detections on a very large scale. And again, Schaff and Waldhauser have shown the way forward with some key answers to how to generalize, taking into account those 2 features, sparse network and cross-correlation as a detector in a paper published in December 2010, as you see the title there. And in particular, to me, I think so important, with a group of events in the Parkfield region, instead of measuring relative arrival times of neighboring events from the local stations, how well can that relative arrival time be measured at regional distances? And although one has to work with a much longer window, and although one has to work with somewhat larger magnitude events to get adequate station-to-noise at further distance, at the magnitude 3 level, the answer is yes, it can still be done with I believe, sub-sample precision of measuring the relative arrival time. From the 2004 AGU meeting was reported work by David Scharf in a similar vein, a case study of events in Liaoning province. And the question is, what is their relative location as seen from a sparse regional network, using the LG waves and cross-correlating between them to get the relative arrival times, highly similar waveforms. But amazingly, those events in Liaoning province from far regional stations could be assigned relative locations at the fractional kilometer level. This is a circle of diameter, radius 1 kilometer, and these events can be assessed then with locations assigned with uncertainty in relative, at least at the 100-meter level. So let's see if we can scale this up. And this is the part of the world that I'm going to focus on for much of the rest of this talk, Kazakhstan. Our group has chosen this in part because in Kazakhstan is published an excellent national bulletin of seismicity. And broadly, we have highly active Tian Shan tectonic earthquakes, also in the Altai-Sayan of southern Siberia. But then most of this region is aseismic from the earthquake point of view, but there's vigorous mining activity, coal mines, for example, in Karaganda. And so let's get into some details here. Looking at a 3-year period, 2006 to 2008, the late event bulletin of the CTBTO has over 8,000 origins in this place. And we will be, in this particular project, looking at signals at the Makenchi array, noting also that the Kazakhstan regional catalog has over 45,000 mostly earthquake events, earthquakes at least in Kazakhstan, but this 45,000 regional catalog does include a lot of mine blasting in these two boxes in Mother Russia. And the computing resources that Sandia has put together to achieve waveform cross-correlation as a detector, running large numbers of templates over extensive, continuous multi-channel data streams, is summarized as having hundreds of cores, over 500 threads with fast communications and so on. So, and this is the kind of results that emerge as reported on Tuesday in a poster. An example, at Makenchi, we see an example of this would be the region for an LG template based on a group velocity window, but in this case it's on the order of 25 seconds wide. And when this, amongst 500 other templates, is run over 3 years of continuous data from this multi-channel array, it picks up itself. This is the autocorrelation. If you've got good eyesight, that's a value of 1 there. And then with degrading cross-correlation, as one goes down here, it's picked up 1, 2, 3, 4, 5, up to it's picked up another 11 events. It's detected them, of which 8 in a previous run were also detected, wherever you see red, with a detector based on the P-wave window. The LG window in the present case has picked up ones that were not detective with a P-wave template. This one, and this one. So this next graphic is for those of you in the back of the room, because there's a lot here, but just look at the big scheme of things. You see the Caspian, this is indeed Kazakhstan, and broadly speaking, in this region, this is a mining region, one sees whole families of events. They are detected. The time of day of these events is shown here, and they all happen in the working hours of daylight. And just from that alone, there's good reason to believe that at most, if not all of them, are mining events. On the other hand, let's take another example. If we go to the Altai Cyan in Russia, somewhat more diffuse, but these are events that are pulled out, and this is presumably a mix of both mining activity and natural earthquakes. Okay. So, preliminary results from this first run here. 3 years of continuous data recorded by a 9-channel array, searched using 500 templates. That computation took 2.5 days. And I say preliminary, the clock started last Friday when this run was made, and it detected nearly 5,000 events, of which a lot were not in the late event bulletin of the CTBTO, and many of them are also not in the regional bulletin, apparently because they originate from mining events, which have been carefully excluded from that earthquake catalog. Okay. So let's go back to some kind of broad issues here. Where are we with all of this? In the year 2012, there have been dozens of studies that have now demonstrated the merits of modern methods of seismic event location by applying, at first, at least 2 features. We'll add a third at the bottom here. Accurate measurement of relative arrival times, and as the poster that David Scharf has this afternoon, of relative sizes of events, neighboring events, at stations in common, relocating numerous events all at the same time. If you worked in this project, as many of you have in this room, my apologies if your name is not in this list, but the main point is to say that a lot of good people have done just terrific work on ever larger scales, studying a particular volcano, studying a particular piece of real estate, and up to California size and getting bigger and bigger and bigger, Kazakhstan. So, and the third feature now beginning to be applied is this use of cross-correlation as a detector. And the big question is whether the methods that work so well at regional scales can be applied across broad areas of active seismicity. Now, Luciana asked a question an hour or so ago about what happens when you have an event in an aseismic area. This method isn't going to help you for that. But most busy places with lots of earthquakes, when you set up networks and you record that activity and you run them for 10, 20 years, almost everything you record today from that region you've more or less seen before. And how do you use that historic data to help you work on the signals or whatever you record for the 24 hours of today? And, you don't have to wait for computers to get any better. They're good enough now to do this. You can put enough of them together, and this is what computers are for. So we're working through, I'm sure others are doing this too, to try and address this big question. How can this be made to work? And if we can do it, then the age of precision seismology will have arrived. And this is my summary statement. We can do this if we so choose. Thank you.
Thank you, Paul. It looks like we have plenty of time for questions from the floor.
I couldn't hear a key word there. Do I think what?
Crowdsourcing.
I have no knowledge of crowdsourcing, so that shows you I can't really help you on that. So there's questions about what level of sophistication in processing. The first talk in this session from Stuart Russell showed the great benefits of working with can I fairly summarize them as kind of envelope functions where you don't bother about every little wiggle. I think cross-correlation works so well and does just such a superlative job, not for all events, but for a large fraction of them, that I have to learn more about crowdsourcing, apparently.
Any other questions? Well, then, thanks, Paul.
Sure.
We'll move on.
Yep.
Yeah.
Steve, this is your pointer. The button's there.
Okay. And am I going to operate off of the keyboard?
Right. So use the 4 keys in the middle pad there.
Okay, I'll just use the keys.
You click the mouse.
All right.
Okay, our next talk is combined use of absolute and differential seismic arrival time data to improve event locations. The talk will be given by Stephen Myers.
Thanks for the opportunity to give a talk today. As we've seen before, there are basically 2 types of data that are dominantly used to locate events. One is traditional pick time data, of which places like the ISC have decades and decades of archived arrival time picks. Others are differential times based on cross correlations and other methods. And what I'm going to talk about today is a little bit of the detail of what we've seen in previous talks in terms of how we can bring these 2 types of data together, but also importantly about how they should be separated from one another because they really have very different error structures. So the first thing I want to give an advertisement for Doug Dodge's poster this afternoon, which is an effort to do the cross-correlation of a massive global data set. It has over 2,800,000 distinct events, 166 million distinct waveforms, and after a full waveform cross-correlation between events that are close to one another, he finds that there's about 188,000 distinct events, as shown here in a density plot that can correlate with one another with a regional and global bulletin, and also that there's about 4 million correlation pairs. That work is focused on detection, but we can also use this kind of data set with differential arrival times on phases to build a very rich correlation data set which has been pointed out in previous talks. So fundamentally, these massive, huge data sets are made up of differential time or correlation pairs. And what I want to do is just step through what these correlation pairs look like. So we always start with an individual waveform. In this case, it's a nuclear explosion recorded at the Mina station in Nevada. To that, we might add another event. This is another nuclear explosion. It's a few kilometers away from this one. These 2 events are very similar. The correlation coefficient over a 110-second window is 0.37. And in order to align the first P's, we'd have to shift the whole thing by about 1.8 seconds. So this is the fundamental basis of how we might discover events that are correlated with one another. But this doesn't give us the full information of correlated phase picks that we need to relocate events. So based on that initial correlation, we then window some phase windows. And here we see PN, PG, LG, and then in a different frequency band, the surface wave. And after windowing those and doing the correlation in individual windows, we see that PN correlates, that's cross-correlation coefficient is 0.93, but it's also a very short window because PG arrives right on its heels. And we had to shift it a little bit based on the pick times, but not much. PG correlates quite well, 0.77, but we had to shift a little bit more. LG, this is something we see with a lot of nuclear explosions. LG doesn't correlate very well for these events, and we had to shift it almost 4 seconds to make them align. And then the surface wave, which we find to be very important for these kinds of data sets, correlates the best, 0.998, and we had to shift it about 1.7 seconds. So these differences between arrival times relative to that first arrival is what we're going to base our correlation or differential time data sets on. And what you do is you would just repeat this process for a given pair of events at a bunch of stations. I apologize, this looks like it's a little bit faint, but this is the result for the two Korean tests, 2006 and 2009, went through, and this is the regional stations. MDJ, for instance, we found a good correlation for PN, PG, and RG. Some of the other stations in the region, really all we could get was PN to correlate. And then a global set of stations, we also found good correlations for the P waves. And these are just some examples. Again, MDJ, PN, pretty high correlation coefficient. RG, again, you're up at 0.9, almost perfect correlation, and then PG. So what happens if we go ahead and relocate do a relative relocation based on these differential time picks? We get a result that's very similar to some published studies. For instance, this Wen and Long paper in 2010, and also Selby, where the 2006 event is south-southeast of the 2009 event, separated by about 1.78 kilometers. And the statistical significance is there that these two events are not in the same spot. This is a very nice relative relocation. That has a lot of information in it itself, but in nuclear explosion monitoring anyway, absolute location is really important. So what happens if you just use a differential time data set to locate this? There is a little bit of information in the relative picks just because they have different slownesses. And if you plot out the region that these differential time picks can fit and characterize it as a Gaussian, you find that it could occur, those two pairs could occur anywhere in this region in a statistical sense, and it would fit the data just fine. So the absolute location you're going to get out of an event pair is not terribly good unless you have a lot more events to work with. So then we're back to using the absolute time picks. What would happen if we did that for these two events? This is 2006 here, 2009 here, and just picking the P waves and first PN regionally and P globally. This is just an example of one station in North America where the 2006 event, that's the pick, 2009. And I really held it to just the waveforms that I thought were really clear. Anything that was at all ambiguous, I threw away. And if we do a relative location of these in an absolute sense, we can get a pretty good location. What I've plotted here, again, blue is 2009, red is 2006. And these are the locations, these diamonds here from Wen and Long, where they did a relative relocation and then they fixed the 2006 event at a position based on satellite imagery. So theirs is not purely a seismic location. So, but just using absolute time picks, we can get pretty good locations. There's a 5-kilometer bar here. The relative positions aren't the best, and importantly, if we look at those uncertainty regions around this, they're pretty big, and statistically you can't distinguish whether they are individual events or not. So what we'd like to do is combine these two types of data in a statistically rigorous sense and see whether we can maintain the relative location precision and have it help the absolute time or absolute location also. And we've done this by working or extending our Bayes-Loc program. Bayes-Loc is fundamentally the formulation of the joint probability over the multiple event location problem. Without differential time picks, we've published this in 2 GJI articles in 2006 and 2009. That first version of the code is available. It's open source. It's on SourceForge at that URL if you'd like to use it. But ultimately, what we'd like to do is we have a bunch of arrival times, whether they're differential or absolute, and we'd like to determine a lot of information from that. We'd like to get event locations. We'd like to get corrections to travel times. We'd like to estimate the precision of the measurements. And we'd also like to determine whether the phase labels were picked properly or whether some of them are just simply erroneous. And this is, with the exception of the green, this is what we published already in GJI, and the green is what we've added to this. And this is just the statistical formulation of what I set up here. We would like to determine the probability of origin times, event positions, travel times, phase labels, pick precision on differential times, precision on travel time corrections, just given the arrival time data, the differential data, and input phase labels. And as we saw before, you can take these kinds of statistical equations and turn them around into forward problems using Bayes' theorem. And this is the equation you saw previously. And then we get a series of forward problems. This is the probability that you have the arrivals that you observed given a bunch of event locations and travel times and their precisions. Here's the thing we've added, which is now you've got to fit the differential travel times given the event positions and their estimate of uncertainty, and on down, including, this should actually say these should be priors on all of these positions. So this is all great, but how does this actually work? Everybody always looks at this and says that's wonderful, but they don't have a good feel for how you actually solve this. Well, the way you solve it is to, well, actually before that I'm going to get into just the formulation of the differential arrival times. It's extremely simple. The way we predict the differential arrival times is just to subtract the proposed or current state of an origin time for event 1 and event 2, plus the differential travel time between event 1 and event 2, and that's going to give us our predicted differential time. The observed differential time is the absolute time in epic seconds of the two arrivals, in this case based on waveform correlation. And then we're going to model the uncertainty or the variance of the observed minus predicted as a precision parameter. And that precision parameter has a phase component and also a component that scales the correlation coefficient. And both of these parameters, the phase component and the correlation component, are modeled during a Markov chain Monte Carlo. Now I'm going to get to how we actually sample this. And what I'm showing here is a movie. Each of these points is a starting position for an event. Each of these is a residual for PN, PG, and LG. These are NTS, nuclear explosions, and the known position are in these little triangles down here. And what we're going to do is propose a new position for these things and determine whether it's more probable or less probable. If it was more probable, we accept it, and if it was less probable, then we might accept it at the ratio of the two probabilities. And if we go ahead and run this, you can see how this quickly, the events rapidly go to the neighborhood around the actual locations. The residuals go down in level. These are picks that were determined to be junk, and it relabels a few, and it marches around the known location, and how the distribution of points around that gives you the uncertainty. Now this is returning to that slide you already saw, which is the North Korean tests. These are based on satellite location. These are the ones with absolute time picks. If we add differential time picks to this and run it through that Markov chain Monte Carlo procedure, here's the difference. And so just toggling back and forth, now all of a sudden the relative positions are very consistent with other studies and our own on relative location. And very importantly, the area, for instance, of the 2006 air ellipse is 11 times smaller. And for the 2009, it's about 4 times smaller. And it's statistically consistent with what we got from satellite locations. So we think that we're preserving the accuracy while still reducing the uncertainty dramatically. Another thing that you can do is look at the relative position of each event, and these are now, all these little dots are Markov chain Monte Carlo samples of the relative position. Now this pattern could you know, this could be here, and then that would make the 2006 event here. And what you find is that this pattern just marches around that whole uncertainty ellipse. But because of the additional data modeling we do, potentially scaling the uncertainties, what we find is that by mixing the two types of data, we actually reduce the relative location error. Also, if you recall, when we did this without the absolute time picks, the uncertainty was about 350 meters. Now it's about 200 meters. So this goes back to what Paul showed, where using regional and teleseismic data, we can get relative position on the order of hundreds of meters. So in conclusion, adding differential time measurements to conventional picks results in absolute locations that are conditional on the precise relative location. That's what you saw in this picture. And constraining relative event positions reduces absolute and relative location uncertainties. And in some instances, we actually find it improves location accuracy as well. Thank you.
We have time for some questions. Any questions from the floor?
So the question is, what about the depths? We do get slightly improved depths when we just used absolute time picks. What we found was that the MC samples extended throughout the crust. When we do the differential time, it's constrained to be in the upper crust. So it's plus or minus 5 kilometers or so. So it doesn't tell you that, I wouldn't base a discriminant on event depth based on this. The depths are a little bit better, but it doesn't solve the problem. Thanks.
Any other questions? Thanks, Steve. Okay, our final presentation for this session is high-resolution earthquake catalogs for Southern California and Hawaii from waveform cross-correlation, and the presentation will be given by Peter Shearer.
Is there a pointer?
Yes, it's right there. And the button is up here.
Okay, well, thank you for the opportunity to speak in this session. What I'm going to describe is the results of two collaborative projects that I've been involved in. One to relocate seismicity in Southern California, that's in a collaboration with Caltech, and then one to relocate seismicity on the island of Hawaii, that's in a collaboration with HVO and the University of Hawaii and University of Miami. So I think by this time in the session, I think you all know the answer to this. But I have this slide, so I will show you. This is focused on the local earthquake location problem, where the location uncertainty, the scatter in the catalog locations, is usually on the order of 1 or 2 kilometers. So if you see a feature like this, you see a cloud of points that has a width of a few kilometers, and you don't know what the underlying structure is. And there's a lot of possibilities. You see below that if you were to convolve those with a 1 or 2 kilometer location uncertainty, you would get what you see on the top. So we are clearly going to learn a lot more about faults and fault structures and things if we can improve the location accuracy. And this has been known. I will focus here on improving the relative location accuracy, as I think the majority of the talks here have. And this has been known for a long time. The way to do this, at least for small clusters of events, and it goes back to the master event method and others. But then more recently, this has started to be applied to larger and more distributed sets of seismicity. And of course, the most well-known of these techniques is the double difference method of Waldhauser and Ellsworth. I've been more involved in an alternate technique that we call the source-specific station term approach, but they do a very similar thing, which is allow you to improve the relative location accuracy of nearby events, and in some sense to correct for the unknown effect of a three-dimensional velocity structure without actually solving for that 3D velocity structure. But then combined with that, you can apply those methods just to the phase picks alone. But if you combine that then with the precision that you get from waveform cross-correlation, which has already been mentioned a number of times, you get a much further improvement in the relative location accuracy. This is a cartoon that just shows if you have two events that are quite close to each other, that what you will commonly observe is when they're recorded on the same seismic station that their waveforms are quite similar. And this is the case. It's much more so when you have closely spaced events than if you try to, for example, cross-correlate the same event at two different seismic stations. So in this case, we have event 1 and event 2, and you'll see small time shifts that you can resolve when you do the cross-correlation, and those more precise time shifts then will translate into more precise relative locations between the events. So you see an example here from Southern California, event 1 and event 2 at station A, event 1 and event 2 at station B, etc. The waveforms don't look very similar at all among the stations, but between those two events are very similar. So in this case, you can compute a cross-correlation function which has a very well defined peak that's a measure of the differential time. Okay, so as I mentioned, we're involved in two large-scale relocation projects. One is in Southern California, and we have a waveform archive online at Caltech. You can see some of the numbers for how many cross-correlations we've done. We've released a series of relocated catalogs that you can get at the SCEC data center. The latest of this is the HYS catalog that goes through June 2011. More recently, we've begun a similar project for the island of Hawaii using the HVO data, and we've computed a new relocated catalog, and we just submitted that, and the first version of the relocated catalog will be available soon. So now I just want to show some examples of the location improvement you can get. So this is for Southern California, and we're looking at the southern part of the Salton Sea. And this is now showing the various stages of location improvement that can be achieved. So these are the original catalog locations. If we use a 3D velocity model, if you do a joint hypocenter velocity inversion, you can improve the locations a fair bit, but you get a larger improvement in the relative location accuracy when you apply the source-specific station terms. So what you see here is sort of the limit of what can be achieved with the phase picks alone, and I think it's important to realize that one can achieve quite an improvement in the locations without doing the waveform cross-correlation. But in order to get that final sharpening of the locations, you need to do the waveform cross-correlation. I will say in a little bit later that, of course, one of the things you want to do in the cross-correlation is you want to cross-correlate events that are close to each other. So in doing so, it's helpful to have as good a catalog as you can. So it's a good idea to first relocate the events using the existing phase picks as best you can, and that helps you to choose the events to apply the cross-correlation on. So just in this case, you can see, for example, this wide zone of seismicity called the Brawley seismic zone. You can now see it's a series of conjugate faults along here. If we look at a cross-section along the Brawley seismic zone, we can see we also get a considerable improvement in the depth of the events. So the original catalog locations are widely scattered in depth, but you see at the end we have actually quite a, the seismicity is confined to a very narrow depth range. Okay, now if we turn to the island of Hawaii, I just want to highlight this region of seismicity that's between Mauna Loa volcano and the Kilauea caldera, shown there. Now if we look at the original catalog locations, they're the small red dots, they're kind of hard to see. This is a map view, a north-south cross-section and an east-west cross-section. And now if I go to the relocations, you can see how much things will sharpen up. So if I toggle back, catalog locations, new locations, catalog locations, new locations. So there's a huge improvement. You can see, in particular, the detachment that is thought to be below the main island of Hawaii. Okay, well, I could show more examples of these sorts of improvements, but I thought I would spend the remaining time just to talk about some of the computational challenges that come up. And the first is that at least ideally you'd like to cross-correlate all pairs, but this will scale as the size of the number of events that you have in the catalog. So for a large catalog, that becomes computationally impractical. So of course, the obvious solution is to pick some source radius and then just only cross-correlate events that are within that radius. The approach we use in Southern California is to only select events that are within the 2.5 kilometer radius, or in a region where we have sparse seismicity, where we don't have at least 150 events, we would then go out to a larger radius to get at least those 150 events. So you can see one of the reasons I said that you want to start with as good a catalog as you can, because the location uncertainty in the starting catalog is on the order of 2.5 kilometers. So you want to try to improve that as much as you can to make sure that you will be able to capture those pairs. Anyway, by using this approach, we're able to reduce the size of this problem an enormous amount. So that even though we've cross-correlated 54 million pairs, that's only 0.04% of all of the possible pairs in the catalog. One of the other things that we ran into is that for a large seismic data set, you just have a lot of seismograms. That may seem rather obvious. That's what you want, right? But the problem isn't so much the size of the storage that you need. It's that when you store one file per seismogram, it's not a very efficient way to do things. You can have problems. You try to make a copy of the archive or to back up the archive. It also will slow the I.O. So the approach that we use is actually to create our own format for this problem where we have one file per event that has all the seismograms for that event, and that will, when you do the cross correlation, then you will speed it because you don't need to be opening and closing as many files as when you have one file per seismogram. And then as Felix talked about, there's also a bit of a problem when you want to update the catalog or move to more of a real-time system. And that is because, at least in theory, if you get a single new event, because all events are linked in some sense to all other events, you should redo the entire problem. But that's not a practical approach. So a more practical approach is to keep the older part of the catalog fixed for some amount of time, and you just then will relocate new events with respect just to the previous events. And then you would, at some regular time interval, say once per year, you would then go ahead and relocate the entire catalog. When you have a very large data set, no matter how high quality it is, you are inevitably going to have some problems in the data. You'll have timing errors or noise spikes or simply poor signal to noise. So it means that some fraction of the cross-correlation measurements you have, even if they have a relatively high cross-correlation coefficient, will be bad. And if you just used a simple least squares approach, that would cause problems in the locations. You want to apply a robust approach. One that we use is based on the L1 norm, but of course you can also have there are a variety of approaches to downweight the outliers that are in the data. And I think I can respond a little bit to the, there was a question from the audience about crowdsourcing, which I think was directed if you wanted to improve the picks. And I don't think that's the way to go, in the sense that if you were to go back and very carefully handpick all the data again, it would make no difference at all, and you would have wasted a huge amount of time. I think it's the cross-correlation is where you get the big improvements. You simply cannot time the phase pick arrivals much better than they already have been by the station operators. And then I think it's also useful to be aware that the waveforms that you have online can be used for more things than simply doing the cross correlations and improving the location. So it's nice if you can design your waveform archive in a way that will facilitate those projects as well. And I can give a couple of examples. Well, I guess I'll just give the one that I said on the second one. What we do is we routinely compute the spectra for the body waves, and then we have a method that has some similarities to the source-specific station term approach that gives you a spatially varying empirical Green's function that you can use to correct the source spectra and then use a theoretical source model to estimate the stress drops. So this is just showing our preliminary results for Hawaii, showing the single event stress drops, and they're colored here where red are the lower stress drops and the blues and purples are the higher stress drops. You can see there's a lot of scatter here, but you also see some spatially coherent patterns, areas of higher and lower stress drops. I'll highlight one that's near the Kilauea volcano, and it seems that there is this linear feature here tends to have much higher stress drops than this linear feature here. We still need to confirm that this is a robust result, but if it holds up, I think it's certainly saying something about the tectonic conditions that this seismicity is taking place in. So just to summarize sort of the last half of my talk, some of the computational challenges, you want to design the waveform database for fast I/O. It's good to use robust processing methods. There should be some kind of plan to have a regular updating of the catalog. And I also think it's useful to keep in mind that these waveforms can be used for a lot of things. So thank you.
Questions?
Is ready for lunch?
So, okay. Well, thank you very much, Peter. Thanks again to all of our presenters, and I wish to remind you that we have a poster session this afternoon, S43G. There are 10 posters that expand on many of the themes that you saw in the oral presentations. So thanks for attending.